Hello, everyone. Today, we are going to discuss Chapter 5, Section 2, Development of Smart Contracts. In the previous section, we have already covered the relevant definitions, architecture, and operating mechanisms of smart contracts. In this section, we will focus on how smart contracts are written. Smart contracts can be classified into three types based on the programming language: script-based, Turing-complete, and verifiable contracts. Each type of contract has its own applicable language. For example, Bitcoin's script language, used in script-based contracts, is a stack-based, reverse Polish notation simple execution language. The design pattern of script languages is very simple, similar to embedded devices. The script instructions, called opcodes, are divided into constants, key operations, number operations, etc. Bitcoin's script language contains opcodes that lack the ability for loops and complex flow control and can only execute a limited number of times. This avoids issues like infinite loops or other logical errors caused by programming mistakes. Ethereum's Turing-complete language, introduced by Ethereum founder Vitalik Buterin, supports Turing-complete smart contracts. There are three main programming languages: Solidity, Serpent, and Vyper. Solidity is the contract programming language in Ethereum, which is compiled into EVM bytecode and runs on the Ethereum Virtual Machine, EVM. Serpent is a contract programming language similar to Python. It uses LLL compilation and is also ultimately compiled into EVM bytecode. Vyper is an upgrade of Serpent with a primary focus on simplicity and security. The second type is verifiable languages, such as Pact. Pact is similar to the Haskell language and is the programming language for Kadena blockchain smart contracts. This type of language is mainly used in high-security and high-efficiency commercial transaction scenarios. It consists of three parts: tables, keep, sense, and module, which are responsible for contract data storage, contract authorization verification, and contract code management. Like script-based languages, its logical structure is Turing incomplete and does not support operations like loops and recursion. For example, the smart contract language in Hyperledger Fabric, also known as Chaincode, is generally written in Go, but it also supports Java and other programming languages. It is a Turing-complete language. Its main features include good concurrency mechanisms, simple design, embedded C language support, error handling, and automatic garbage collection. Now we compare various programming languages. Compared to other smart contract languages, Solidity is more active and widespread. It also adds attributes related to Ethereum transactions and supports more general computing. Vyper, on the other hand, is built on Solidity but drops features like modifiers, contract inheritance, and inline assembly. While this avoids some vulnerabilities, it also introduces other issues. Bitcoin scripts consist of two parts: instructions and data. The supported instructions are fewer than 200, making the development process relatively simple. However, because it doesn't support loops, conditions, or jumps, the logic it can implement is quite limited. The Pact language features keyset-based validation modes, allowing for a wide range of transactional applications. It is a non-Turing-complete language, omitting features like loops and recursion, which makes it easier for manual verification and auditing. Hyperledger Fabric smart contracts run on Docker and can be written in general-purpose languages like Go and Java. Cardano smart contracts run on the Docker virtual machine, using high-level programming languages like Docker for contract development. Both Go and Java are typical Turing-complete high-level languages, efficient for communication but difficult for beginners without development experience. Based on the virtual environments where smart contracts run, they can be divided into three categories: embedded execution, virtual machine-based execution, and container-based execution. The mainstream smart contract platforms currently are Ethereum, Hyperledger Fabric, and EOS. Ethereum primarily uses a public blockchain model, where every node in the system can read chain data, send transactions, and confirm transactions. All nodes can participate in consensus. Relatively, it has low threshold, allowing anyone to become a system node. Hyperledger Fabric, on the other hand, uses a permission blockchain where only specific nodes with permission can join the network, and only certain nodes can maintain the ledger and participate in consensus. EOS also uses a public blockchain model, but it improves network throughput by leveraging graphene technology and parallelizing the network. The differences in blockchain types and operational mechanisms lead to different operating mechanisms for smart contracts on different platforms. Among them, Ethereum, Hyperledger Fabric, and EOS have the most representative smart contract operating mechanisms. In Ethereum, smart contracts are primarily executed through the Ethereum Virtual Machine, EVM, running on Ethereum nodes, which interprets and executes the smart contract programs. Its life cycle includes development, compilation, deployment, invocation, and finally, self-destruction. Ethereum's smart contract mechanism involves two types of accounts. One is the external account, controlled by the user's private key, with no associated code. The other is the contract account, controlled by the contract code. Hyperledger Fabric's consortium blockchain project was initiated by IBM and aims to create an open-source specification and standard for blockchain technology. Unlike public blockchains like Bitcoin and Ethereum, Hyperledger Fabric only allows permissioned commercial organizations to share and maintain the network, resulting in a lower degree of decentralization. In Hyperledger Fabric, chaincode has 6 states: install, instantiate, invoke, upgrade, delete, and install. The operating mechanism includes steps such as proposal, packaging, and validation. EOS's operating mechanism is actually composed of a series of actions, where each action represents a contract clause. During deployment, the contract code is sent to the server through client-side commands. In the invocation phase, the client sends action requests to the server using client-side commands. That concludes the content of Chapter 5, Section 2.